So continuing from the last lesson where we look at the construction process of a 5 input, 3 hidden and 3 output neural network, this is the code where we left off. To make it resemble a more real life scenario, we bring in data loader again and we use the Fashion-MNIST dataset. So let's go and fix the imports. Now instead of having all of this, we're gonna just comment all of that out because we want to actually bring in our Fashion-MNIST dataset. So let's go ahead and do that. Remember that this image itself, this is a PL image, so Python imaging library format. We want to convert that to a tensor. So you could use the 2 tensor that will convert the numpy and the array or a PL image and convert that into a tensor. So let's do that. Since we have the data loader, let's also use that. So by using data loader, we put this into the designated batch size. So we're going to set a batch size up here as a parameter, and then we're going to say, okay, so just break them down into this batch size, and I'm going to shuffle them. So now that we have them in batches, let's maybe take the first batch, right? So let's take the first 64 images, and they belong to the same mini batch. So let's take them. Just iterate through that and then just use unpacking to sort of unpack them into train features and train labels. So we want to wrap iterables and want to say train data loaded because that's what we name it in line 15. And let's see what we have now, right? So let's talk about a typical training procedure for a neural network, right? So the first step is usually you want to define a neural network that has some sort of learnable parameters. The learnable parameters, you want to set them to track the gradients. We'll talk about gradients in the next lesson. But in a sense, you want to treat them as hyperparameters that you can fine tune over the training process, all right? Then you want to iterate through a set of data, of input. So you want to iterate through the train features and the train labels. In each iteration, you want to basically process the input from the network. So you want to go through this step of like linear, ReLU, linear. And then you want to compute the loss, right? So how far is your output from being correct? Because you want to have the end output is supposed to be a prediction. You want to then track and compute the loss meaning how far are you away from being correct. And then you want to propagate the gradients. You want to adjust the weights. You want to adjust all these different parameters in one direction, taking a small step. And that's something you control through the learning rate. We haven't talked about that yet, but then just give you a general mental model of that, right? You propagate the gradients back into the network's parameters. You adjust the weights, and then you track again and see whether or not the step that you take is taking you closer to a higher level of accuracy, or in other words, reducing your error, minimizing your error. And then you continue this process again. You update the weights of the network, and then again using the same, trying to update the weights as you look at the error. And if you're making more error, then you adjust the weight in the opposite direction, in a different direction. We've seen the syntax using subclassing the neural network.module. And then we initialize the neural networks layers in the init function. This is kind of a basic OOP, Python OOP. If you find this syntax a bit confusing, I suggest you watch my object-oriented programming playlist that's also using Python, so you can get a sense of like what object-oriented programming is. But I assume that you have those basic knowledge, so I'm not gonna dive into that. And this is the example we left with in the last video. So these are very trivial, 5-3 and then ReLU and then another 3-3, right? That's kind of to mimic the one that we whiteboard out. So what we want to do now is to remove all of them and actually replace that with the real layers that is tailored for this Fashion-MNIST dataset, all right? So we have the Fashion-MNIST dataset. 5-3 is not going to work. It's not going to make it because Fashion-MNIST is a 28 times 28 dataset, right? So let's put a note here. This is a 28 times 28. So this is not going to cut it. If you try and do 5-3, then you need to reshape this. You need to reshape the 28 into 5, and which is a bit nonsense. So we don't want to do that. Let's change all of this. You could either uncomment them, or you could just modify them in place. So for example, I'm going to take this. Instead of 5, what do we want as the input layer? Now the input layer would be the amount of neuron, the input neuron, the amount of input neuron. That should just reflect this figure, correct? So let's go ahead and say 28 times 28. The output of this, right? This is the input layer. What about the hidden layer? Now the hidden layer itself, this is something you have to decide, right? How many neurons do you want? Typically you want a figure that is smaller than the input. So you want to have input. If your input 28 times 28 is I think 784. If it's 784, you want a figure that is smaller than that. So you could pick a figure like 512 if you want. You could pick your own figure. This is also something you can learn, I guess. It's something that you can learn and maybe try different kind of grid search kind of method to find a good value. But now we're going to keep 512. So let's go ahead and maybe add another linear layer, because the output of this is 512. This also has to be 512. And this could also be 512. Just keep to the same one. You could add another layer of ReLU just to make it a bit more, with a bit more layers, make it deeper, be able to learn more complex patterns. And then finally, now this is not up to you anymore. This is something that you want to bring in from the last layer. So the last layer would be this is the hidden layer, 512. You want to bring that back in here, 512. And then now, what is the output of that? The output of that should be the number of classes in your test data, in your training data, right? Now in your training data, we have 10 different classes. We have shoes, we have handbags, we have skirts, blouses, all of them, right? And altogether we have 10 classes. So what we want to do here is want to have 10, because this 10 we can then treat it as a probability once we go through a softmax, and then we could see, okay, well, what is the probability of this being a shoe? What is the probability of that being a sandals? What is the probability of that being jeans, being a t-shirt? And altogether we want 10 of them, because we want to have 10 different sets of probabilities, and they should sum up to 1. So this is kind of how a sequential network looks like. Let's take a look at a forward pass. Now, because this series is about training on GPU, and later we're going to build projects using GPU training. So if you don't have GPU, that's fine. If you don't have a CUDA compatible graphics card or device, that's fine. But if you do have one, then I want to show you how to use that. So I want to say something like GPU for training. And you could move them to device. We haven't had device. You can define device in here. We could define that all the way up there. Else, want to say if there is it's not available, just use CPU. Same thing in here, you could just move them to device. This is still going to work even if you don't have a GPU, because it says first, if torch.cuda is available. If that's true, then just use CUDA. If not, just CPU. So it wouldn't matter. So this is fine. This is all we need to do. You don't have a compatible NVIDIA graphics card, that's fine. You could still use CPU, right? So we're going to print a model. All of this looks to be okay so far, but we haven't really made one prediction. So let's go ahead and just make one prediction. So let's just go ahead and say y hat, and we're going to say model. Y hat is kind of a convention for us to say that we're predicting y. So this is estimates of y. If you're saying y hat, it's like estimates of y. X hat, estimates of x, right? So we're going to say y hat, just estimates of the true value. And we're going to say model, and then what are we going to pass in? We pass in our training features. So these are the training features, right? And we're not really using train labels, so I guess you could put an underscore there, and let's run all of this. So I want to set up your virtual environment, make sure you have all of this is working, hopefully. So let's go ahead and say Python -i, why not, neural2.py. Fingers crossed we're going to see, okay, so that's the neural network there. So we first say that it's going to start off from the flatten. So that's the first step. It's all part of the neural network, all of this, but the sequential comes after the flatten process. Okay, just to remind you a bit of what the flatten layer is doing, what this is doing, right? It takes this, it converts the each of your 28 times 28, your two-dimensional 2D image. It converts that into a contiguous, did I spell that correctly? Meaning touching, right? Next or together in a sequence, touching, right? So into a continuous array of, you want to take these two multiply together, I believe it's 784 pixel values. That's what it is doing, right? So give you a quick example of that. Also, by the way, when you do this, the mini batch dimension at dimension 0, that is actually maintained. So let's give you a simple example, right? So let's go ahead and say input. I'm going to say torch.rand. Let's just create some random numbers. I'm going to say, let's say 3 images, each of them being 28 times 28, right? So torch.rand, 3 images, 28 height, 28 width. So let's run that. If I take a look at my input and I specifically look at the size of my tensor, I will see that my tensor has a size of 3, 28, 28, no surprise. But if I create a flatten, let's go ahead and say flatten layer. You could say flatten layer if you want to, or you can just say flatten, and that's going to just take in from nn.flatten. Then what I'm going to do is I'm going to flatten that, and so I have a flatten input, or you can say flatten image or flatten input, and then we just call your flatten onto your input. All right, so we basically take an instance of the nn flatten, and then we call it on the input. Because we don't name it flatten, we name it flatten layer. Now, if we take a look at flat_input.size, we see now we go from a 3 2828 to 3 784. So notice that the mini batch dimension, the 3 doesn't get changed. It's still maintained there, right? 3 is still 3. The only one that gets changed is the 28 and 28. It takes that and it converts that to a contiguous array of 784 pixel values. So going back, this is the neural network. It starts with the flatten process, which is to take 2828, convert that, and then it starts with the linear, which is defined in here, then the ReLU defined in here. We've learned about ReLU in the last lesson, right? The rectified linear units. We spoke about that before. Now, this is to introduce some non-linearity. You can also use the sigmoid function. Some of you may ask, like, why would you use ReLU versus sigmoid function? And why is it that a lot of the state-of-the-art neural networks, they use ReLU instead of sigmoid functions? But I'm going to give you a short form of that. The reason you use ReLU over, say, something like sigmoid function to introduce non-linearity is you also introduce you add some sparsity in the activations. So what is sparsity? Sparsity is when your weights are not activated, right? They are below 0 because of the ReLU. So you want to have something like, for example, Wx, that's your weight, plus your biases, plus B. You want it to be something like below 0. So that doesn't fire. So when you introduce some sparsity, the more such units that exist in a layer, the more sparse the resulting representation, because that means that not all of your neurons are going to fire. Not all of them are going to activate. And that would also result in a less likelihood to overfit and also a faster training. And the reason for a faster training, this is maybe a bit subjective, because in the grand scheme of things, it probably doesn't matter that much, because you probably have a lot of GPU and a lot of computational resources to use anyway. But the reason why it's a faster training is because ReLU really just performed this, right? It performed the max 0x. It says that if the value is below 0, then just use 0, because the maximum of 0 and x. If the value is -3, use 0. But if the value is 3, use 3. So you just pick the maximum between 0 and x. So this is actually a really, really fast operation. It's not performing any kind of expensive exponential operation if you compare that to using something like Sigmoid, for example. But if you're actually interested in that, you could maybe ask me in the comments. I could talk a little bit about that and go into the theory and be more academically rigorous about my explanation. But now I'm just trying to keep it simple. So really, you don't really have to worry too much about all of these things that I just mentioned there. You will want to check at least that the in features, you say that initially you want to accept 784. That's correct, because you flatten them into 784. Then it outputs 512, pass that into the hidden layer. Now in the hidden layer, you have to take 512, because this is what the output of that would be. So you want to take 512, then you output 512 again. And so this also have to take the last one of this 512. It has to be sequential in this way. And then you have to output 10, because you want to treat them as probabilities. You want to take them and then pass it into softmax, and then just get the a list of 10 probabilities. Okay. Now what about the PyTorchViz that we bring in? If you want to follow along this part, then what you want to do is to just do a quick installation to install Torchviz. So you do that by doing pip install Torchviz inside your virtual environment. All right. And I already have that done, so I'm gonna go ahead and just say from Torchviz import make dot. So this is to bring in Torchviz. This is a visualization tool for PyTorch. There's a lot of other visualization tool for PyTorch, but I'm used to this. I can maybe talk about the other options later on, but for now, in this part of the series, we don't want to diverge too much from there. So Torchviz, that's a visualization tool for PyTorch. It visualizes the computational graph of your neural network model. So we could actually try to get a graph from what we just created in here. All right, this could be very helpful for debugging. If you want to follow along, just make sure you install that, and then just doing a pip install Torchviz, and then come back to this video. So to create that is actually pretty simple as well. So what we need to do is to just call make dot, and we could start with a y hat. This is the prediction. So this is what it goes through. It calls the model, and this is going to be visualized. So we want to set up some parameters. So let's create a dictionary for the parameters. We want to say model dot name parameters. So what this will do is to find all the name parameters, and it would just use them as a value to this params argument. You want to render them and give it a title. So you could say just render it as neural network if you want to just be a bit simple, and just give it a format of PNG, for example. So let's save that. Notice that the forward pass is really what's doing most of the work here, because initialization is just defining that, right? So for example, you call self.flatten. This flatten doesn't exist until you define that. And here, we're defining in here. So this is what gives the flatten that behavior. And then the self.linear value stack, this is also something that is, it doesn't exist until you define them, and you define them in here, right? So when you initialize this, when you create an instance of this, instantiate this, flatten and linear value stack is created, but it's not being called. They are just definition. You're not running it. You have to do it with forward, and then forward is being called because of the model. So let's make sure all of this still works. Let's save it. Let's go ahead and say Python -i newer2.py. Let's run that. Okay, everything still works, but now you should also have a PNG file in the same directory. So let's open that up. This is it, nn.png. You can also take a look at this file itself. This will tell you the graph. How do you create the graph? And if you don't want to see this, you can close that out and use the PNG. And this is what you have. This is what was created for you. So let's spend about 5 minutes here to take a look at what PyTorchViz has created for us. I'm going to zoom in a bit. So this is the computational graph of our neural network. You have the blue boxes here. The blue boxes are the parameters of the model. So we're trying to learn the weight. We're trying to find the right figures, the right numbers for the weight, right? The one that minimizes the error. This is the weight, this is the weight, this is the weight, and these are the biases, and the biases. If you were to put them side by side, you should see that they conform to the same dimensions that you defined in here. So 512, 784, this is the 784, this is the 512, and then from there on, you have the bias, 512 and 512. That's because of the layers. You need 512 biases, 512 biases. And then the weight is what you define in here, that's the linear. And same thing in here, 512, 10. This is also what you see in here, 10 and 512, right? So the blue boxes are all just the parameters that you're trying to learn, all right? Your weights and your biases. Your weights and your biases, they are the blue boxes. And the values that you'll be updating, these are the values that you'll be updating during your training process to make accurate predictions. So you want to update these figures in here. The gray boxes are the operations that are applied to your tensors, all right? So these are the gray boxes. If you pay attention to the label here, you see that the backward, the reverse operations are also shown in the graph. These are the functions that are applied in the forward direction, but it also knows how to compute its derivative during the backward propagation step. So let's not get overwhelmed. I'm going to keep that image there. I'm going to zoom in a bit more, and I'm going to give you some simple examples before we go back to this image. So suppose I create a simple torch, create some simple random numbers, and I'm going to put requires grade equals to true to keep track of the gradients. Now this is a simple addition, right? I'm taking a random number 1 plus random number 1. So when I'm doing this, I'm adding a tensor plus a tensor. If I run that and I say x, and I look at the grade function, you will see that there's an add backward, right? And you see that there's also like something like add multiplication backward, ReLU backward. So this is what we're talking about earlier. Is that the functions, even though they're applied in the forward direction, it also knows how to compute its derivative during the backward propagation step. And a reference of that is also stored in this. So you could say grade underscore function, and you will see, okay, this operation is done. I could sort of reverse this process, and I could do that only if I store the function that leads to the result, right? So if to get this result, for example, from x to this result is actually a summation of these two. In order to get to this result, what have to happen? So this is the function, and it's actually stored in there. And so it actually give you this information as well in the graph. So this, in this case here, because it's an addition, it says that's the add backward, all right? I'll give you another example. Maybe I'll try y now. I say torch random, and let's put a random number. Let's just say put two numbers. I want to say requires equals to true. But this time, let's go ahead and just say take this and just sum it, right? So if I run y, you see that there is a sum backward, right? So it knows that in order to arrive at this figure, a summation has been performed, right? So it basically, instead of a add backward, it's now a sum backward. If you replace the sum with a mean, you run y, you see now this is a mean backward, all right? What about let's take a look at something like a multiplication backward, right? Let's take a look at, let's say, what is y? Let's go ahead and just create two new ones. Torch.random, say 2, 2. Y equals to, guess it could be the same, 2, 2. All right, now we create z. Let's do a matmul, matrix multiplication. So let's say torch.matmul x, y. If we print z, well, notice that z doesn't really, let's take a look at whether or not it has the function, grad function. And if it doesn't have, it's because we didn't ask it to track. So yep, there's nothing. So the way we should do it is we want to pass in requires grade. So this will tell you to track the gradient. We do the same thing for y. pass true as well. And now we do z. If we print z now it's starting to track the gradient function. Earlier it wasn't tracking that. Now it's tracking the gradient function because we asked it to track, and we do that by using requires grad equals to true. And now you see mm backwards. That's a mat mul, right? So this is add and mat mul. You see that there's accumulating and then add mat mul again, right? So to summarize, every time you set requires grad to true, you're actually keeping track of the operations, all the operations that are performed on the tensor. So if you do x and then you say requires grad equals to true, you're asking to keep track of all the operations performed on this tensor x. And this is good because it automatically compute the gradient during the backward pass later, and so that you can perform the optimization. We'll talk more about automatic differentiation and gradient tracking in the next lesson, but for now, let's focus on the forward pass, and let's know that automatic differentiation is what allows our neural network to back propagate the error, because towards the end, you still need to look at the error. You still need to take that and then compare that to the true label and say, okay, well, this is your y hat. What about the true prediction y? Right? You need to compare them, and then using that, you compute an error. You said, how far away are you from the truth? How far away are you from being correct? And then take that error, you need to back propagate the error back all the way up here, and then change the different blue boxes, meaning change all the different weights and the biases. So more formally, you're saying that you're back propagating the error, computing the gradients of the weights, which is here, the blue boxes, as long as the biases with respect to the loss function. So want to compute how far away are you from the truth, take that loss, and then back propagate it. Notice as well that in the final one, that this is the output of the model, the output of this neural network, that's a 64 and 10, right? Now 10 itself, this is the 10 that is going to come out from your network, the output of your network. These are all logits, right? These are all log of odds. So in our earlier lesson, the log of odds is what we use as an input to yet another thing called a softmax function to convert the log of odds to probabilities. If you want to rewatch that lesson, go ahead and rewatch that. If you're not familiar with what a log of odds is, how do you convert that to probabilities, you can rewatch the earlier lesson. And what you can do with make dot as well. Let's close the, let's actually, maybe we can keep that, or we can just close that out now. You could also maybe have a few more information by asking it to show attributes and set that to true. And you can also ask it to sort of show safe equals to true. That's whether to display safe tensor nodes. So you can also set that to be true. Give it a different name now so that we don't overwrite our first image, first graph. Let's quit that out now. And let's run it again. So now you should see a different kind of visual because now you show attributes equals to true. Let's open that up. Now this is a bit more, so compare them, put them side by side. So this one has more information. This is with the show attributes equals to true, right? So this is a bit more simplistic. This is a bit more simple. This is with showing attributes, so you can also compare and see if this confirms to your expectation. So really, really good for troubleshooting, especially if something goes wrong in your training process and you're realizing that you have some sort of data leak or that all your models is predicting with an accuracy of 0 or something. You could maybe just use a tool, a visualization tool like Torchviz or something else to visualize the computation graph, right? And we'll come back to this. We'll use this a lot actually over the next few lessons of the series. If there's a visualization tool that you'd like me to use, maybe put them in the comments and I'll see them and I'll read them and I can consider them. But I'm more familiar with this one, so I'm sticking to this. And that's where we're at for this lesson. And we're getting quite close to learning all of the basics, because once we're done with the basics, we want to start building stuff with it, right? We want to build cool stuff if we want to do real life projects and not just learn about the theories. So we're getting quite close now. The next lesson, we're going to look at automatic differentiation. We're going to look at optimization. And then we're going to learn about saving the model so that we can pre-train a model and then pass it on to someone. But once all of that is done, we start to go into some real life projects. So thanks for joining in. I'll see you in the next lesson.